We are going to have an introduction to rates of reactions. So this is also called chemical kinetics, but we just want to talk a little bit about the basics. So what do we mean by a reaction rate? You probably can tell that a rate is referring to how fast something is going, how fast something is happening. A reaction can happen very quickly or very slowly. Here I have a reactant going to product, and you can measure how quickly or slowly it's happening by measuring the change in the amount of reactant that you have. As it goes away, it can go away quickly or slowly. Or you can measure the change in the amount of product that you have. That can either be produced quickly or slowly. So here I have a little everyday example of frosting some cupcakes. These are supposed to be cupcakes, and then these are frosted cupcakes. That's the product. This is the starting material or the reactant. So you could either measure how quickly the unfrosted cupcakes are going away, or you could measure how quickly the frosted cupcakes are being produced. So it's easy to visualize how a cupcake gets frosted, but how does a reaction take place with some really tiny reactants? And the theory for collision theory, it's just a theory to try to explain how we see these changes in molecules. The molecules or the particles have to come together and collide. You can't have two things reacting together if they're on complete opposite sides of the test tube or beaker. So they have to collide. They have to be aligned in the proper way when they do collide, because there might be a bond that's breaking or forming. If the two things that are supposed to be involved in that bond are not close to each other during the collision, then that bond might not form. And then also the collision has to have enough energy for this transformation to take place. If a bond has to break, that takes energy. So the collision has to have enough energy to let the reaction or the transformation occur. So here, let's look at these energy diagrams of reactions. We have the endothermic reaction, where overall the change in enthalpy is positive. The products are higher in energy. And we have an exothermic reaction where the overall enthalpy change is negative. The products are lower in energy. However, the intermediate for the reaction is a little bit unstable. Usually you have to go through some sort of unstable intermediate in a reaction, and so you do have a hump to get over. Whether you're going uphill or downhill in the end, you still have a little bit of energy that needs to be put in to the reaction to get it to go. You can think of this as the energy needed for the collision to happen and be able to reach the intermediate that leads to the products. And I labeled this H because this is the change in enthalpy that can be positive or negative. And I labeled this one A because this can be known as the activation energy. So the energy needed to get over that initial hump or barrier. So here we have quite a large one, and here we have a smaller one. And so we might expect this one with a smaller activation energy to proceed a little bit more quickly. All right, even though we can't see these molecules colliding, we can use this collision theory to help us explain and remember what can affect the rate of reaction. So collision theory gives us a helpful model for being able to remember what affects reaction rate. If we think of all these as molecules that are undergoing collision, we can see that if we need more collisions, having more molecules, higher concentration of the reactants is going to make more collisions happen. So kind of like cars on the road, if you have a lot more cars on the road, you have a traffic jam, you're going to have a greater likelihood for collision. And then temperature is how fast these molecules are moving, the average kinetic energy of the molecules. And so if you picture again the cars on the road, if everybody is speeding, in addition to having a crowded road, if everybody's speeding, then the likelihood that collisions are going to happen is going to go up, and then also these collisions are going to be more serious and dangerous. So the molecules colliding are going to have a greater likelihood to have enough energy to do the bond breaking. I can't think of a way to compare surface area to a traffic jam, but if you are breaking up a solid into a lot of pieces so that you increase the surface area, then that is going to make the reactions with those solids faster. So let's try to think of a quick comparison for this one. So it's like if you're frying something on a pan and you want to make sure that something is cooked. If you have one big chunk, that's going to take longer to cook than if you have a bunch of little pieces. It's going to be easier to cook all of these because, you know, there's a lot more surface area. There's no part that's too far from the frying pan, and so it's going to happen faster. Another thing that speeds up reaction rates is a catalyst. So what a catalyst is something that kind of stabilizes or lowers the energy of this high energy intermediate. So instead of having to have this reaction proceed over this really huge hill in this intermediate, if we have a catalyzed reaction, the catalyst stabilizes. Now we have a new intermediate that's lower in energy, and so the hump that the reactants have to get over, the hump of energy, the energetic hump, is lower. So this is our new activation energy. It's less than our old activation energy, and it's easier to get over a small hill than it is to get over a bigger hill. So if you were trying to roll something up a hill, it would be faster if the hill were a little bit shorter. I have a comparison that I sometimes use in case people are new to the concept of a catalyst. So instead of a chemical reaction, let's take something that's easier to visualize. 2 boards and 3 nails are coming together to make this product. This would be a very slow reaction if you had to just try to push the nails through the wood with your hands. So what we need here is a catalyst of some sort. And a lot of times in chemical reactions, the catalyst is listed over the arrow because it's not really a starting material or a reactant, and it's also not part of the product. All right, so I've tried to draw a hammer. So this will definitely make the process go more quickly. It's going to make it easier and lower in energy to be pushing those nails through the board. That's the high energy part, is having those nails being driven through the board, and that's difficult to do with just your hands. It'll be a lot easier with a catalyst, with a hammer, but the catalyst, even though it's needed for the reaction, it's not really one of the starting materials, and it also doesn't end up attached to your product. And you can use it again. So once you've made one of these, you can't use these boards or these nails to make another one. You'd need more boards and more nails, but you wouldn't need another hammer. You could use the same hammer to do the reaction several times. So that's the same thing with a catalyst. You can use the same catalyst to process a whole bunch of reactants into products and to do it more easily and more quickly than would happen without the catalyst. I guess if we went back to our car analogy, this would be like driving a very weak car. So a low speed collision is enough to wreck the car, whereas with a stronger car, you'd need a higher speed collision. So if your goal was to have a collision and wreck the car, then having a weaker car is going to help out with that. Okay, so that red line that I drew is kind of already the answer to this first part. I can't really fit it on the screen with these questions though. So the second line that I drew, the line that I drew in burgundy, was the line to represent the catalyzed reaction. Remember that that line led to an intermediate that is more stable, lower in energy. And remember that the activation energy was smaller or lower. However, if you look at that graph, you'll see that the change in enthalpy overall is the same because you start in the same place and you end in the same place. So that change in energy is going to be the same whether you take a path with a high energy intermediate or a path with a lower energy intermediate. Where you end up is the same and where you started is the same, so the delta H is the same. There's no change in that. So let's review how each of these changes would affect the rate of this forward reaction. So if we are adding more NO, nitric oxide gas, we are increasing the concentration of the reactants. It's like putting more cars on the road. So this would have a faster reaction rate. If you decrease the temperature, that's like slowing all the cars down in your traffic jam, so the number of collisions is going to decrease. So that's going to decrease the rate. If you are removing some of the hydrogen gas that is needed for the reaction, it's kind of like taking cars off of the road. You're going to have fewer collisions. So this is also going to decrease the rate. And then adding catalysts always increases the rate. It makes things go faster by stabilizing that intermediate and lowering the activation energy. So this would have a rate increase.